Here's our PLC code and PID settings for our Tesla turbine. We have three blocks of code. One is copying the RPM sensor output into the process raw variable in the PID. The second is the output control into the flow control valve, depending on what the PID system needs to control the process variable. And finally, the last one is the process variable into our DF15. Now going into our PID setup. For the general tab, we have C, DS, and DF memory allotted. The C is for binary on or off actions. The DS is for the integer values that are used throughout the tuning, and the DF is for the different calculations that are used to get the PID values. Going to the set point now, we have a lower limit of 0 and an upper of 100, and this is also the same later on in the process variable tab I'll show. For the error term, we have square and deadband error both off, since neither one is needed for this application. Square error is usually used for systems that use liquid, and the deadband is when you don't want your system to be extremely reactive to error around the set point. Onto the loop algorithm now. We have the proportional, integral, and derivative gain that we found from manual tuning. To get the values for our manual tuning, we use Ziegler-Nichols tuning method. So here's our picture that we used, a snapshot of our first tuning. So we have the proportional set to 20, the integral set to 6,000, or anything close to infinity, and then the derivative to 0. So we were testing it at a set point of 40, which got us this curve here, or this cycle, and we were able to get data off of it, and we managed to read 6 cycles in 20 seconds. So we plugged this in to the ultimate period calculation. This is also the 20 that we get from the proportional gain that we used for it. So the ultimate period is the time divided by the cycles. That's 20 seconds divided by 6 cycles, and that ends up with 3.33 seconds per cycle. So we use that to plug into the Ziegler-Nichols PID tuning parameters. So we do the 20 for the ultimate gain divided by 1.7 gives us 11.76 for the proportional, and then we do 3.33 divided by 2 to get us the integral value, and then we take the ultimate period here divided by 8, which gives us 0.41 for the derivative value. So after we got that and plugged it in, then we did some fine-tuning with the system in place to make sure that the curve is as good as it's going to be, and then it responds more effectively after a load is applied and then removed. So we have a proportional gain of 9, the reset time for the integral 1.5 seconds, and derivative gain at 0.35 seconds, and the sample rate at 100 milliseconds. We have anti-windup on so that we don't accumulate error. Derivative gain limit is off. We have direct acting so that when the system has an error that is positive, then it needs to increase. And then bumpless transfer is in mode 1. For the output, we have from 0 to 100%, and we have PWM control off because it is not needed, and the PWM control is already done through the Arduino before it enters the PLC. For the process variable, we have from 0 to 100, which matches our set point 100%, and we have a filter of 5% because of the interference that is within the system itself. Then here's our wiring setup. and pressure setup, air pressure setup. So over here on the PLC, we have the power ran from the power supply, which is plugged into the outlet. We have power going directly out of the top of the power supply into the proportional valve control, which the white wires run to the proportional valve, and that is hooked up into the control, which goes into the PLC. And then out of the PLC, we also have the Arduino wires going into the Arduino, and we also have the positive, negative, and communication for the RPM sensor set up here, which then is set up with the USB that goes through there and then into the back of the computer to give us our RPM reading. And then for the pressure system, we have the shop air supply into a manual valve that we have set at about 105. And then that goes into the proportional valve that's controlled by the PID. And that goes into the top of our Tesla turbine, which then controls the PID control. Here's our test of the Tesla turbine. We have the PLC controls running with the PID. Here's our values currently. We have the set point at 30 with our manually found values for the PID control. So we'll start by bumping it from the 30 set point to 40 to show how it reacts. Now it's starting to settle down. So now that we have it at the 40, we're going to add some disturbance to the system to show that it can compensate. Holds on pretty tight. There we go. And our last show is going to be with the Arduino spitting out the RPM.
Just to show you how fast we can go with this setup, I'm going to set the valve to 100%.
Right around 8,000.